I was advised to open a presentation with a promise. So here it is. Prey size change was a major driver of human evolution. Barkai and I argued in a recent paper in Quaternary that Homo erectus specialized in hunting large prey, and that later, during most of the Pleistocene, large prey abundance declined. This decline caused energetic stress. Many key phenomena during prehistory, like the expansion of the human brain and various cultural changes, can be explained as adaptations to cope energetically with prey size decline. Why hunt large prey? We argued, based on paleobiological and other types of evidence, that humans were hypercarnivores that specialized in large prey. Firstly, large prey hold a higher portion of the herbivore's biomass. On the top left, Hemson et al. Reconstructed the biomass density of megaherbivores in Africa 1,000 years ago and found that it was several times higher than the biomass density of smaller prey. Today, in some reserves, elephants compose 80% of the herbivore's biomass. Secondly, megaherbivores do not escape. On the top right, based on Hirt et al. 2017, megaherbivores' maximum speed is lower than that of a lion. Thus, as Churchill found in 1993, hunting of megaherbivores do not require complex projectile weapons. Thirdly, larger animals provides higher energetic return. The chart on the bottom right is based on data from Kelly 2013. Finally, but possibly most critically, fat. Hypercarnivorous humans needed fat to overcome the protein constraint that Speth described in 1983. Ledger 1968 is the only sizable relevant dataset, and it clearly shows that larger animals, especially above 200 kilogram males and 150 kilogram females in square B, contain more calories of fat than of protein. Each of the four reasons has energetic repercussions on humans that hunt and consume prey, so a decline in large prey abundance should lead to energetic pressure. Why don't we find more large prey? Methodological practices, taphonomic biases, and the incorrect use of ethnography all obscure the true importance of large prey. Zoo archaeologists often ignore prey mass in their analysis. We analyzed 60 Hadza hunts that were recorded by O'Connell and Boone's teams in the mid-80s. The NISP abundance index of the giraffe, for example, was 7%, while the giraffe's actual biomass contribution was 57%. Additionally, 3 out of 11 giraffes didn't contribute any bone to the assemblage. Thus, several times larger animals, like elephants, are expected to rarely show up in open central place and cave assemblages, which have the highest visibility in the record. The 4 largest prey animals in the Hadza assemblage in the black columns are ranked highest. They have contributed 90% of the assemblage biomass. Other researchers have also found, based on a very large ethnographic dataset, that humans prefer to hunt larger prey. We know that the ranking follows the energetic returns. Thus, the data contradicts recent attempts to first estimate the energetic returns and then predict ranking. Another practice that distorts the importance of large prey is comparing cut marks. On the left is the decline in NISP with prey size in the Hadza assemblage. Less NISP per animal means a lower probability of identifying cut marks. Moreover, cut marks rarely appear in very large prey. On the right is a photo from a recent paper by Haynes and Krasinski showing an elephant bone after professional field butchers removed the meat. Periosteum and large mass of muscle and cartilage prevents creating cut marks. Even if cut marks were created, their preservation is minimal in open sites. Also, megaherbivores are hunted by disadvantaging, and thus the final dispatch can be done by the initiation of bleeding with a wooden spear or a sharp stone without leaving marks on bones or stones. If Homo erectus became a large prey predator, as we have argued, we would expect to find fewer cut marks in Homo erectus sites compared to early Homo sites. Ethnography distorts the importance of large prey. Present ecosystems are not analogic to Pleistocene ecosystems. The Hadza territory in Tanzania is depleted of large prey like elephants, rhinos, and hippos, which leads to increased energetic costs of hunting relative to gathering. Also, the removal of elephants enabled the abundance of baobab trees, an important source of nutrition for the Hadza. Both fruits and seeds are consumed, and most of the honey is obtained from bees that reside on top of the baobab trees. Elephants dislike trees, and they particularly dislike baobab trees. In game reserves, the recovery of elephant populations was associated with a marked decline in baobab populations. Elephants would have also competed for berries that at times provide most of the calories to the Hadza. Metal arrowheads and the use of the bow itself were not available to humans during at least 98% of their 2.5 million years of evolution. Without these tools and materials, it is doubtful that the Hadza would have survived in a territory that is so depleted of large game. Prey size declined throughout the Pleistocene. Paleontology provides a deeper time perspective than archaeology. According to Felicia Smith and colleagues, the mean size of terrestrial mammals grew almost unabated for 62.5 million years, but in the last 2.5 million years, the mean size declined to a level that was last prevalent 55 million years ago. The question is, what were the dynamics of the decline? The number of large herbivorous species declined in Africa beginning almost 5 million years ago and continued to decline throughout the Pleistocene. Faith et al. Claimed that the human contribution to the decline began with Homo sapiens, but from the data one can also associate Homo erectus with the decline. A decline in mega-herbivores took place throughout the Pleistocene, and the decline in size 4 and 3 herbivores started 1 to 1.5 million years ago, accompanied by an increase in the number of size 2 species. In the Levant, we analyzed the faunal record of 133 archaeological layers from 58 sites, Dembitzer et al. 2022, and found that a statistically significant prey decline took place throughout the Pleistocene. We could find no association of the decline with climate changes. Here is what I did for this talk. To test the association between prey size decline and cultural changes, I compared the prey size between several late Archean and early MSA-MP herbivores assemblages where data was readily available. In this case, beside the cultural change, we may also be looking at the appearance of two new species, Homo sapiens and Neanderthal. I compared the percentage of MNI of over 1,000 kilogram herbivores, that is, megaherbivores, to total herbivores, since their decline points to a need for a new hunting technology to hunt escaping herbivores. Jeff Smith and colleagues claimed in 2019 that the prey size decline in Africa is an artifact of the higher number of cave sites in the late Middle Pleistocene. However, the causation may be reversed. Humans may have occupied caves because of the switch to smaller prey. I compared just open sites of late Archean to early MSA in South Africa. The decline in relative MNI of megaherbivores in open sites is more than 50%, from over 20% of to less than 10%. In Olorgesailie, East Africa, there was also some 50% decline in the MNI of megaherbivores between the late Archean and the MSA. The decline from the early Middle Pleistocene level 6.2 of Grandolina in Atapuerca, Spain, to level 10.1 of the late Middle Pleistocene was also close to 50%. Level 6.2 contains remains of Homo antecessor, presumably the ancestor of the Neanderthal. Level 10.1 is attributed to early members of the Neanderthal clade. Bollamore cave levels belong to MIS 9 to MIS 5E, so in this case, the second half of the Middle Pleistocene. A decline in megaherbivores is noticeable concurrently with the increased use of Levallois. Lastly, Ornac 3 in southern France represents an MIS 9 to MIS 8 transition between the Archean and the MP. Levallois became dominant in levels 1 to 3 with a decline in megaherbivores. The decline is in elephants and rhinos, whereas large bovids remain at 32% of the MNI. Of course, to be more conclusive, studies will have to rely on larger datasets, like the one we used in the Levant. By the way, apart from East Africa, I couldn't find any description of climatic development that may have caused the decline in the other sites. Prey size decline led to cultural change. To support the causation of the associations, we proposed a mechanistic explanation. This chart is from our paper on the Levant. Wooden-tip thrusting spears were suitable enough to dispatch disadvantaged megaherbivores during the Archelian, when megaherbivores provided most of the biomass, but stone points were necessary to economically subdue a higher portion of evading large prey, like bison and horses, during the Middle Paleolithic. Projectile weapons were necessary to economically acquire a higher portion of smaller, faster targets, like gazelle, during the Upper Paleolithic. Later, an even higher portion of smaller prey required dogs and traps to hunt energetically efficiently. And finally, to the subject of this session, cultural and behavioral changes that are caused by prey change support our contention that carnivory played a dominant role in human subsistence. The probable human contribution to the prey size decline provides additional support.